Hi there, welcome back. Having discussed forces from magnetic fields on moving charges and then from magnetic fields on currents, now we're going to look at if there is a force between two current carrying wires. Specifically, we're going to take two parallel current carrying wires and understand why they apply forces on each other. We will see when these forces are attractive and when they are repulsive. The answer might surprise you a little bit. And then what the magnitude of these forces are. Okay, let me take two parallel wires. There's wire 1 and here is wire 2. They're parallel to each other. They carry different currents, I1 and I2, and let's say the distance between them is D. In this case, I have taken the currents to be in the same direction. We will do the other condition later. And we want to understand if there is a force between these two wires and why and whether it's attractive or repulsive. Okay, we already know everything we need to know to figure this out, so let's build it out one step at a time. So each of these currents will have a magnetic field. Every current has a magnetic field, you remember that. And so I'm going to use my first right-hand rule to figure out the direction of the current. So if I hold my right-hand thumb in the direction of I1 and let my fingers curl, my fingers will look like this. And so the magnetic field from this current is going to be coming out of the page at the top and going into the page at the bottom. Simply a consequence of the first right-hand rule. So it doesn't only come out of the page near the wire, it also does farther away. So I can draw more of these here. Yes, it does get weaker in magnitude as you go farther out, but the fact is it's going to keep coming out everywhere above the wire, and it's going to keep going in everywhere below the wire. So I can show more of these here. So these magnetic fields shown with the red color are from current I1. And for current I2, they are external magnetic fields. And we saw in the previous video that an external magnetic field applies a force on a current, and let's say in this case the length of the wires are L, so that would be the length of the overlap of the external magnetic field and the current. So there will be a force on I2 from the magnetic field of I1, and since the magnetic field of I1 is going into the page in the vicinity of wire 2, we can use the second right-hand rule to figure out the direction of this force. So to use the second right-hand rule, I will have my thumb pointing this way in the direction of current, I2 now. And then all my fingers will be lined up next to it here, and all of them are pointing into the page or into the screen to represent the external magnetic field going into the page. And so when you hold your right hand like this, you see that your palm is over here. And so the force is going to be in the upward direction. And since the current model looks at a flow of positive charges, we don't need to reverse anything. So to show the force of I1 on I2, it'll be like this all along the length of the wire. So I'm going to label this as F1 on 2. Let me write down what F1 on 2 is. You could call it force from I1 on I2. That would not be incorrect. It is for the force from one current on the other. But more technically correctly, as we have seen here, it's force from the magnetic field of I1 on I2. So current I1 has a magnetic field B1, and that magnetic field B1 has a force on I2. So this magnetic field here that's shown in red is B1. Let's now see what happens to the force from I2 on I1. You may already have some expectations because those would be Newton's third law pair of forces, but let's see what it is. So to do that, I have to figure out the external magnetic field from I2, which again, using the same right-hand rule, the current is in the same direction, the fingers will be curling the same way, so it'll be dots above the wire. No matter how far I go, it'll be dots. I'm using the color purple to represent the magnetic field from I2, and then it'll be X's below the wire so I can show some excess here. So yes, this picture is getting a little bit crowded, but hopefully you are seeing based on the color coding that the magnetic field of current I2 is shown in purple and the magnetic field of current I1 is shown in red. So now we are interested in figuring out the force on I1 from B2. So these purple guys here are B2. And so in this case, I have the current going in the right direction. The magnetic field is coming out of the page. So I will have to hold my right hand with the thumb pointing in the right direction, but then my fingers next to it are all pointing out of the screen to reflect the direction of magnetic field B2 in the vicinity of current I1. And when you hold your right hand like this, you see that your palm is down, and so the palm's facing is down this way, which would be the direction of force. So the force on I1 from the current in I2, or more correctly from the magnetic field of current I2, is going to be in the downward direction. So I can label these arrows as F2 on 1. So there are two things we can talk about here. F1 on 2 and F2 on 1 are Newton's third law pair of forces. So they must be opposite in direction, which they are as we see above, and they must be equal in magnitude. We haven't gotten to magnitude yet, but we're going to check that in a second. The other thing that you might find surprising here is that when you have two wires with currents in the same direction, they attract. So far, every time we had something in the same direction or same pole, it was always repulsive. And then when it was opposite directions or opposite poles or opposite charges, then it was attractive. But in this case, it turns out that that relationship flips on itself. And when you have two wires with currents in the same direction, they attract. And I will leave it as an exercise for you to try what would happen if you change the direction of one of these currents and make them go opposite. They will repel. So currents in opposite direction will repel. So if I had a wire with I1 in that direction and I2 in this direction, the force would be this way. This would be F2 on 1, and this would be F1 on 2. So once again, they are opposite in direction and equal in magnitude, so they do follow Newton's third law, but they repel when the currents are in opposite direction. You can do the same exercise we just did to confirm that for yourself. Okay, lastly, let's talk about the magnitude. I'm going to erase these things here to clear some room to discuss the magnitude of these and see if they will be the same. So the magnetic field at wire center of wire I2 from I1, let's see what that would be. We know the equation for that. The magnetic field of a current was mu naught I over 2 pi r, where r was the distance from the wire at which we wanted the magnetic field. So in this case, I have B1 at this point, wire center of I2. B1 is going to be mu naught times I1 over 2 pi d, because d is the distance from wire 1 to wire center of 2. And then we just did in the previous video, the force of a magnetic field on a current was given as ILB when they are perpendicular to each other, which in this case they are. So my force 1 on 2 would be I2LB1. So I'm looking at the force of magnetic field B1 on current I2. So that's what that would be. And I can substitute B1 from top and rearrange this to get mu naught I1 I2L over 2 pi d. All I've done is plugged in B1 from here for this B1. This is not a new equation. You can always do this as a two-step process if you needed to work it out on a problem, to figure out the magnetic field first and just use your basic equations, which are this one and this one. So those are the only two that you need to know, and those are the only two I'll give you on tests. This is just a consequence of putting those two together. And when you do that for the other wire, when you want to figure out the magnetic field here at wire center of wire 1 from current 2, you will get B2 equals mu naught I2 over 2 pi d. And then when you put that together to get force of 2 on 1, it would be I1 L B2, and B2 would simply be mu naught I2 over 2 pi d. So when you substitute that, you will once again get mu naught I1 I2 L over 2 pi d. So you see that their magnitudes are equal, they are exactly the same, and their directions are opposite. All right, so we covered a few things here, basically reviewed a number of previous things we have been doing to figure out what the force between two current carrying wires will be. So we saw that two current carrying wires that are parallel to each other do apply forces on each other. The magnetic field from each wire acts as an external magnetic field for the other current, and so it applies a force on it. We saw that these forces are indeed third law pair of forces. And then we saw a little bit of a surprising thing, that these forces were attractive when the currents are in the same direction and repulsive when they are in opposite directions. So this was a little bit of a surprise based on previous things we have done, but that's the way it works out. We saw what the magnitude of forces were. They were equal from 1 on 2 equals to 2 on 1. And we saw that the force is directly proportional to the two currents as well as the length of the wires that are overlapping, and inversely proportional to the distance between the wires. Thank you.